All right, so I'm just going to walk through this review. Feel free to watch, try the problems on your own. If you get stuck, maybe you can look at one of the explanations. Hopefully it's helpful. So we're looking at integrals involving e to the x and a to the x, and also integrals whose result are going to be the natural log or an inverse trig function. So we want to just kind of be able to play around with these different things and determine when it would be best to use each method. All right, so looking at this first problem, looks like I've got 1 divided by a linear function. So anytime you've got, a linear function that's been plugged into another function, so really what I have is I have 2x plus 5 that's been plugged into the 1 over blob function, right? I've replaced it in there for 1 over blob. So that looks like it's going to be a natural log. And then if your inner function is linear, you can simply divide by that slope to undo the chain rule. So this is just going to be the natural log of the absolute value of 2x plus 5, but then divided by 2 to undo the chain rule. Because if you're taking the derivative of this, you'd be multiplying by 2, which is the derivative of the inner function. We're going to divide by 2 to undo that. So we end up with b. Number 2 gives you an indefinite integral and a u, and wants to see what this is equivalent to. So let's see what would happen if we started with u equals x to the 1/2. Then we would find du dx, which would be 1/2 x to the negative 1/2. So du dx would be 1 over 2 root x. And that means that dx would be 2 square root x times du. So if we plug that in for dx, and we plug this in for square root x, we will get antiderivative of e to the u over root x times 2 root x du. Of course, we're only going to plug the u in to this root x in this case. Okay, our root x's are going to divide out as desired, and we end up with an antiderivative all in terms of u. 2 times the antiderivative of e to the u du. And that ends up giving us c. For the third one here, kind of, I can see my options here are some natural logs, some arctans. For arctangent, you're looking for something like 1 over 1 plus x squared, or maybe 1 over a squared plus x squared, something like that. This doesn't really look squared to me, so I think it's probably not going to be arctan. I'm also looking for things where maybe if I took the entire denominator here, is the derivative of that up top? And the answer is yes. So I'm thinking this might be a natural log, because it kind of looks like 1 over blob times the derivative of the blob. So let's let u be 4 plus e to the x, the denominator. Then du dx is going to be e to the x. So dx is going to be du divided by e to the x. So if I plug u in for 4 plus e to the x, and du over e to the x in for dx, I get the antiderivative of e to the x over u times du over e to the x. E to the x's are going to divide out. I get the antiderivative of 1 over u du. And that's just the natural log of absolute value u plus c. Replacing my u, I get ln absolute 4 plus e to the x plus c. And done. Let's see, that's D, I guess. All right, So number 4, I have e to the 2 ln x. I'm feeling tempted to do some simplification because I have an e and an ln, and they are inverse functions. So maybe I could simplify this. So how about e to the ln of x squared, right? Because that's the power property of logarithms. If a natural log is multiplied by 2, I should be able to make that a power inside. And then that just becomes the antiderivative of x squared dx, because e to the ln, they undo each other. And then it becomes a very straightforward integral. It would just be x cubed over 3 plus c. So I end up with b. So a little algebraic simplification makes that a much easier problem. Okay, here we have a version of a to the blob. And the blob is linear. The inside function, the inner function, is 2x. 2x has been plugged into 3 to the blob function. So I know that the antiderivative of 3 to the 2x is simply 3 to the 2x divided by ln 3. But then I also need to divide by 2 because that is the derivative of 2x. So I'll just remind you for this that if I had the antiderivative of 3 to the x, that is simply 1 over ln 3 times 3 to the x. Since I have a linear function inside the 3 raised to something function, I get 1 over ln 3 times 3 to the 2x, but I also have to divide by 2 in order to undo the chain rule that would happen if I took the derivative. So that is going to simplify to 3 to the 2x over 2 ln 3 plus c, which is this answer right here. Of course, I could also write it as 3 to the 2x over ln 9 plus c, but I don't need to in this case. Okay, moving on. All right, so I might be tempted by an arctangent because I see that x squared plus 9. So that kind of looks like an arctangent problem. But if it were x squared plus 9, it would need to be 1 over x squared plus 9 in order for me to be tempted by arctangent. Since I have x in the numerator, I think I can just make this a u substitution problem. So let me let u be x squared plus 9. Reason being is because x is a multiple of the derivative of x squared plus 9. So now I have du dx equals 2x, and therefore dx is equal to du divided by 2x. Plugging things in, I get the antiderivative of x over u times du over 2x. My x's will divide out, and I'll end up with 1/2 times the integral of 1 over u du, which ends up being 1/2 ln absolute value u plus c. Plug my u back in, and I have 1/2 ln absolute x squared plus 9 plus c. Now, the reason the answer does not have absolute value is because x squared plus 9 is always greater than 0, right? So I don't need to worry about keeping the absolute value there. And that gives me this answer right here, part A. Okay, now 7 looks a bit more like an arctangent problem because I have 1 over 1 plus something squared. So I'm going to rewrite this as antiderivative of 1 over 1 plus 4x all squared dx, right? That's the same thing. And so, again, this is basically an arctangent function with a linear, or the derivative of an arctangent function with a linear function plugged in. So I can find the antiderivative normally. It would be arctangent of 4x. But I need to divide by 4, again, because that's the derivative of the linear function. So I'm really undoing the chain rule. And that's going to give me b. Okay, here I've got a bit of a definite integral. So I need to think through this a little bit. So what I'm thinking is that I've got a tangent and I've also got a cosine squared in the denominator. But another way to write that would be 0 to pi fourths times e to the tangent x secant squared x dx, right? Because if I have cosine squared in the denominator, that's the same as secant squared in the numerator. So now what I have is I have a function that's been plugged into the e to the blob function, and I have the derivative of that function, right? And multiplying by the derivative of tangent x. So I am going to let u be tangent x in this case, so that du dx will be secant squared x. Because I just have this secant squared dx, I'm just going to solve for du in this case, just a slightly different method, and just say, oh, du and secant squared dx are the same. So I should be able to just replace secant squared x dx with du. If you want to solve for dx, you can also do it that way. Because it's a definite integral, I'd like to change my limits of integration. So if x equals 0, then u equals tangent of 0, and tangent of 0 is 0. If x equals pi fourths, then u is tangent of pi fourths, which is 1. So my new limits of integration are going from 0 to 1. So I will go from 0 to 1 of e to the u du. No problem. So that's just e to the u evaluated between 0 and 1, which is e to the 1 minus e to the 0, which is e minus 1. So I end up with D for my final answer there. All right. Indefinite integrals. So if I wanted to anti-differentiate cotangent x, I would simply write this as cosine x divided by sine x. You always want your u to be the thing in the denominator so that you're multiplying by the numerator in this case. We wouldn't want to have u be cosine x. We want u to be sine x, so that du dx is cosine x. And so we can rewrite this as, let's see, we could solve for dx if we want. Dx would be du divided by cosine x. So if we plug that in, we get the antiderivative of cosine x over u times du over cosine x. Those divide out. And now I have antiderivative 1 over u du, which is ln absolute u plus c, which is going to give me ln absolute sine x plus c. Okay. Number 10. It looks like I have e raised to something, and then I also have maybe the derivative of that thing. So what if I could rewrite this as e to the x to the negative 1 times x to the negative 2, and that will look very much like x to the negative 2 is the derivative of x to the negative 1, or very similar to it. So if I let u be x to the negative 1, then du dx would be negative x to the negative 2. So dx is du divided by negative x to the negative 2. Plugging that in, I get the antiderivative of e to the u times x to the negative 2 du over negative x to the negative 2. These divide out, and I'm left with negative integral e to the u du, which ends up being negative e to the u plus c. So I'll end up with negative e to the 1 over x plus c. Okay. Let's see about 11 and 12. So 11 looks like I have e raised to a linear function. Anytime you have e raised to a linear function, you can use linear shortcut here. So I'm going to first pull the 3 out front and just have e to the 4x minus 5. Antiderivative of e to a linear function is e to the linear function divided by the slope of that linear function, or the derivative of that linear function, plus c. So I would probably write this as 3/4 e to the 4x minus 5 plus c. And finally, 12, before I maybe pause and get a little more power, though I guess I still have 16%. 1 plus sine squared. And then I have cosine x. Well, what I'm noticing is that I have 1 plus something squared, and then I also have its derivative. So I'm wondering about an arctangent situation. I don't want to just let u be 1 plus sine squared x, because then du dx would be 2 times sine x times cosine x, which is not what I have up here. So I don't want to do a u substitution. I don't think that's going to work. So I think maybe instead I'm going to write this as antiderivative of 1 over 1 plus sine x all squared times cosine x dx. I could keep the cosine x in the numerator, of course, but I just want you to see that it's really 1 over 1 plus something squared. So I think this is going to end up being an arctangent problem. Let's let u be sine x. Then du dx is going to be cosine x. So dx will be du divided by cosine x. So since dx is du over cosine x, I can plug everything in and get the antiderivative of 1 over 1 plus u squared times cosine x times du over cosine x. Cosine x's will divide out, and now I just have an arctangent problem. So I'll get arctangent of u plus c, which should be arctangent of sine x plus c. Seems like my iPad is lagging a bit here. So I'll pause the video here and do the rest of the problems a little bit later.